All right, welcome back. Now with me on stage is Thomas and Marius. They will talk about SIM hacking. I'm very excited. So please give a warm round of applause, and the stage is yours.
Hello, everyone. I hope you all had a great lunch and are all ready to join us for our SIM Hacking Odyssey. This talk will be a little bit of a run-through over the multiple years we've been working on hostile SIMs and using SIMs for hacking. So let's dive into it. Before we start, I'm Marius. I'm currently working as an assistant professor at the University of Birmingham. That's Birmingham, UK, not Alabama. And I focus in my research on a lot of low-level, deeply embedded security things, so embedded systems, and most importantly, mobile security and cellular security here.
Hey, I'm Tomasz. I'm doing a PhD with Marius, same university, not in Alabama. I do a little bit of demo scene work on the side, and I generally just focus on like low-level hardware and software.
Yeah, and the journey we have today is roughly 4 years in time and starts off in 2022 when we developed SWICC and SWSIM. Then 2 years later, we followed up with CATana, with SIMurai, where we looked a little bit more into hostile SIMs. We had some accidental lock screen bypasses on Android along the way in 2025. Then we equipped the CATana to the SIMurai tool in 2026. And last, we give a little out view on what we are working on now, so what will likely be coming out this year, next year, or in the following 2 years, somewhere around. Now, before getting started, we want to quickly acknowledge that we are not the first, hopefully not the last, persons working on the field of SIM security. There has been a lot of fantastic talk and fantastic work before in the field, including here Troopers in 2019. So if you want to learn more about the topic, I would recommend to check out all of these talks. And with this, let's get started with chapter 0. We want to emulate a SIM card. Now, how did we come to this? Why did we even want to emulate a SIM? Like, why are physical SIMs not enough for us? And the background of this is in 2022, we were working on releasing firmware, which is a full platform emulation tool for baseband firmware. What does this mean? So usually you have a phone communicating over the air to a cell tower. And for security testing, that kind of works, but is a little bit cumbersome. So our idea was with firmware to take the full cellular baseband firmware located in the phone, write an emulator around it, and run it in an emulation host. So run it on an ordinary computer. Then, instead of connecting it to a cell tower, we would connect a fuzzer to it, delivering the over-the-air input like AFL++, and we were able to find a couple of security vulnerabilities using this approach. This is how it looks in practice. Here, firmware is starting up, and we're replaying one of the crashing inputs we found earlier. This is all great and fantastic, and as said, we were able to find vulnerabilities and get them fixed, but we had a fundamental problem to get into deeper states of the firmware. And the problem is something as follows, right? This picture is actually not complete. When you have your phone talking to a base station, there's a third component. And I guess the talk title gives this away. It's a SIM card. Now, this works fine with a physical phone, right? We have SIM slots. But what about emulators? We don't really have a way to hook up a physical SIM to it. And this is really how our journey started. I thought we need some sort of an emulation stub for firmware so that we can get better states in our emulated firmware, do more security testing. And this was in 2022 when Tomasz and I kind of made first contact. Tomasz one day showed up at my office and said, I need a Bachelor of Science project. Like, I want to finish this uni thing. Can you help me finding a topic? I suggested, hey, wanna build a SIM stub, right? Like just something simple that the emulated baseband thinks we are good. Nothing crazy. A simple SIM stub should be fine enough. And Tomasz said, sure, why not?
Yeah. So how hard can that be, right? Small device, simple software, right? Simple hardware. So that's kind of how it started. I was looking into some standards, and that's usually how I kind of approach these kind of things. And I noticed that actually SIM card is just a smart card. And this is like an extract from one of the like more important specs, ISO 7816, like I think like 13 parts to this spec. Like for example, we start with like electrical contact information, like know where they are, like the electrical information, like what are the signals flowing on these actual wires. Like there's like usually 6 pins. Then you have the actual logical interface, so the protocol, how that looks like. And it turns out that there's like a transmission and application layer, which are actually kind of the same thing in a sense. Then you have some more information about the protocol. Of course, a custom file system with custom file types. And for some reason, there's also a custom query language for this. Like complex lifecycle for the card and also for files and for the file system. You have biometrics. You have also USB. So for example, if you have additional row of pins on your SIM, you might have a USB interface on that SIM. And of course, who doesn't like a nice security boundary?
So in other words, I sent Tomasz on a journey looking into standards for, I don't know, quite some time.
Yeah, the first few months or like half a year was basically just reading specs. So if we actually look at like what a smart card actually does and what it actually contains, it primarily consists of 2 parts. So you have the commands. So that's how the phone communicates with the SIM card. It sends commands out. These are usually structured like this, or actually they're always structured like this. They have a 5-byte header, which is mandatory, which is followed by some optional data, and then the SIM card responds with, or really the smart card responds with status word consisting of 2 bytes and an optional data field. There's some more complexity on the transmission layer, but we will just stay at the application layer today. And this just keeps on going on and on for the entire connection cycle. So the commands come in and then the responses come out. And on the other hand, we also have the file system. So there's a custom file system on the SIM card or on any smart card, and it primarily consists of files and directories, but there's some weird things going on in the directory department, because we also have something called application dedicated files being directories. ADFs are like a special kind of directory, which when you select it, when you kind of enter it, that alters the actual behavior of the card. So if we actually look at the SIM and how that's different from the smart card, like I kind of slipped up saying SIM and smart card interchangeably, and they are really similar. A SIM card is kind of like a superset of the ICC, of the smart card. That's the acronym. And it primarily consists of additional commands. So we have a lot more commands, and these are here, like this is like an extract from the spec, which shows you the different classes and instructions. The first byte of the command is the class, the second byte is the instruction. So this tells you the like within a particular class there are particular instructions, and these are those instructions. And there are also other ones for 2G. This is just a short kind of extract. Then you also have authentication. So of course you want to do authentication to the network. So you need COM128 for 2G and Milanash for 3, 4, and 5G. So you need to be able to run these algorithms, and these are also additional things that are not in a smart card. And then there's also this card application toolkit. You may have seen this, like if you plug in a SIM card that has some additional kind of operator-provided functionality. If you insert this card into your phone, you will most likely see this SIM toolkit app. If you enter that app, you usually see a menu, and this menu is actually fully rendered by the SIM card. And we're actually going to touch on this a little bit later as well. And then there's, of course, the USIM application. So this goes back to the application dedicated file, the special application directory. There is now a USIM directory, the USIM application, which when you go into it, all these features, all this capability is kind of exposed to you. So how do we actually develop this? So we used a pretty simple setup, and we're going to show you how this works. We basically just have a SIM trace. A SIM trace is a simple device that just forwards messages back and forth. So we can run our SIM emulation on the host, and then the messages are going to be flowing back and forth through the SIM trace into a flexible cable that goes into the SIM slot, and then the phone can then see, or really any device on the right, you can see like a more standard like IoT modem. So now we have a short demo of this working. So we're going to start the software SIM emulation on the host. It's going to go through here into the SIM trace, into the phone, over the flexible cable. So that we can see that it actually works.
So we're starting with running software SIM in one of our terminals. Potentially, we start with running PCSCD.
Yeah, PCSCD is a little bit buggy sometimes.
Yeah. And now software SIM is up and running, and it's waiting for an incoming connection. And we start on the other side, the SIM trace software stub. And now SIM trace also is booted up and all ready. And now once we close the SIM tray, sorry, we should start seeing communication flying by. And there we go. This is now the phone communicating with software SIM running on our host. So the phone now thinks a SIM is inserted, it reads data, it reads the files from the file system, and does everything a phone will do really with a SIM.
Yeah.
And that is without having any physical SIM here. So that's how WICC and SWSIM help us to get a SIM up and running and emulated.
Just to like explain a little bit more, like the white bytes are mostly the commands, and then the turquoise bytes are mostly the responses. There's a little bit of mixture there, but that's what you can see there.
So, of course, I mean, this is great, but it has not been done in a single day. Took more like a week, really, after reading all the specs. And I, back in the development time, got constant messages from Tomasz with the update, which was pretty cool because it was not only messages, it was also screenshots and so on. And, well, pictures of phone. So it started almost, or like a little bit more than 4 years ago, where Tomasz just showed, hey, we have our own PCSC interface layer we can use to interact with whatever we will write now. And then he started writing his first SIM emulation stubs, and in the beginning it didn't look well, right? It said unusable SIM card here, emergency calls only. Then it asked about PUC code, so it got a little bit farther, but still doesn't really want to unlock because the PUC mechanism was not implemented by then. It says invalid card at some point. It's really surprising how many failure modes there are and how reliant phone is against not so great SIMs. And then pretty much, not pretty much, exactly 4 years ago, the phone detects that the SIM is there, but says it's not provisioned for calls, okay, or for voice, which probably is fine. At least we have some sort of a SIM. Tomasz also had a small detour, developing a little bit of tooling for showing messages here on an older phone as an example. And then eventually we got to a working setup. Again, almost 4 years ago. In this example, we have one phone on one side being connected to software SIM, attaching to a research cellular network and being fully authenticated, so all the underlying algorithms were run, and it could send SMS to a second phone next to it, which is pretty cool. After that, it was mostly around finishing up, polishing, and so on, and then later on in November that year, we released software SIM publicly.
So after all that, after we had the emulator running, we wanted to think about, well, we were thinking about this already before, but we were thinking, how can we use this for some security research? So we're doing security research, so we want to now use the actual emulation for looking into how this can be attacked. And really, like, we formed an attacker model, which essentially consists of 4 parts. So first of all, we have the software stack. So the SIM card actually runs a card OS. It also can have operator provisioned applications. So all this software can be vulnerable, can have bugs. So, and we've also seen this like before with like the Kaizen leak before. Then we have the physical access. So if you have access to the actual device and the SIM interface, you can exchange the SIM. So for example, you can have a research card with some malicious software that will exploit maybe parsers or other parts of the baseband firmware, or maybe even the application firmware. And then you also have things like interposers, so these kind of thin devices that you can put in between the SIM card and the phone. And again, you can, because the interface there is completely unencrypted and the devices don't authenticate themselves, you can actually rewrite messages. You can also drop messages so they never actually reach the card. And you can also insert new, new responses onto this interface. Then we have the supply chain attack. I mean, this is more relevant for like a state actor, but within the telco world, this is very much relevant. And we've also seen this happen before. Like this is an actual observed like a threat model there, like attack vector. So if you're manufacturing this card anywhere really between the manufacturing, the distribution to the end user, this can really anything can be implanted or altered on that SIM. And then last, we also have the remote administrative features of the card. So even once the card is distributed to the end user, we observed that actually within the spec there's an entire myriad of different capabilities that the operator and manufacturer has to even update the card even once it's distributed. So they can alter files, they can also alter and install applications onto the card. So without user confirmation, you can have a SIM card app being installed on your SIM over the air. And as an interesting kind of view of this, we've also seen like a leakage of some private SIM information from a big South Korean vendor. Okay. So we have the attack surface that we've identified the attacker model that we want to investigate, and now like what tooling do we need? How do we extend the emulation to be able to interact and actually analyze these things? So this is kind of where the SIMurai project was born, and we wanted to combine the software emulation with firmware as well, and be able to do fuzzing with AFL and do other things like that. And then also do some hacky stuff that actually alters the behavior of the emulation. So if we look at the architecture of SIMurai, it consists of essentially this. So we have the commands coming in. This flows into our card reader. So we have like a virtual card reader that the instances of software SIM connect to over TCP. So this is entirely virtual. But more importantly, at the actual host side, it thinks that this is a real card. So it sees this card as if it was connected through a legitimate card reader, like a physical card reader, and a physical card was inserted. And then these commands flow into a DMUX, which then decides how to process these commands. So they can either flow into the software ICC, or they can flow into the software SIM, because again, we have some commands that are still regular smart card commands. Some commands have to go to the SIM card. And then there's a kind of gray area in between where we have to process standardized commands using some proprietary stuff on the software SIM world. We have, of course, a custom file system as well. So we have a kind of way of describing the file system using like a JSON file. So you can easily, like basically on the go, alter what files are in the SIM and how that works. And then as it comes back, as the response comes back, it kind of flows into like this rewrite block where you can end of pipe kind of alter these things if you want to do some really hacky stuff and you don't care about stateful like state of the flow so much. And then this flows out to the device.
Yeah, and with this capability of altering commands coming in and rewriting the responses, we thought, what can we do to showcase that this threat model, this attack vector, is actually there to make people more aware of it? And we thought, let's re-implement parts of SIMJacker. Now, when we say re-implement, we want to be very careful. We are not building any weaponized exploits or tooling. It's really more a proof of concept showing that SIMs can do this and that it's also maybe easier than people think. So what was SIMJacker? SIMJacker was a vulnerability first observed in 2019, which would use a vulnerability in the SIM stack, in the SAT browser, to trick the SIM into issuing proactive commands. Proactive commands will then go from the SIM to the phone, to the baseband, and turn all of this into a spyware. It will send SMS out with the location of the user. So it will retrieve the location using a proactive command and then send a SMS using a proactive command. Unfortunately, these kind of attacks are even still observed today. Just 2 months ago, there was a report on Citizens Lab, by Citizens Lab, showcasing that, that SIMJacker-like attack still exists in the wild. And we set out to just implement the proactive parts of it. So not the initial exploitation of the SIT browser, but just the spyware feature to show locations can be extracted using a SIM. And the main interface for this were proactive commands. So a couple of words what these are.
Yeah, so I said that commands flow only from the phone to the SIM. So how can the SIM actually exfiltrate any information from the device? And actually, there's a way to reverse the flow using we call it, well, in the spec it's called the proactive SIM. So proactive SIM, all that basically is that the SIM card will want to create a special kind of command called proactive command, and then the phone has to request this command then to be executed. And this is the flow of how this looks like. So we have APDUs flowing back and forth. these commands flowing. And really, this can be any command, but the status one is special for the fact that the SIM card can actually configure the phone or the terminal to issue these status commands on a kind of equal interval, so there's like a kind of polling mechanism there. And then the SIM will respond with a special status word, 91XY. Usually, on a success, the SIM card will respond with a hex 9000 response, and that indicates success. And this 91XY is an extension of that. It still indicates success, and if the terminal doesn't support proactive command execution, this will be ignored and it's just considered as success. But in the situation, in the circumstance, which is actually pretty common, where the terminal does actually support proactive commands, this will be used then to produce another command, which is called a fetch, and then it will fetch this proactive command. The terminal will obtain this and execute it and then produce a terminal response. The terminal response indicates a success or failure of processing of this command and any additional information that it wants to transmit to the SIM.
And this is how our re-implementation looks like. We have SIM trays connected with software SIM running, being connected to a phone, and we are rewriting some of the proactive commands to send the according data to the victim phone. Now, we said we're not weaponizing anything, so in this case, the user actually has to click and be giving the consent to have the location stolen. So it's just an SDK app where a user can click.
Application.
Yeah, SIM Toolkit app where a user can click run, and then an SMS would appear to a second attacker phone with the location exfiltrated. So it's this first SMS here with those very weird encoding. It is binary text stealing the location. So this was our proof of concept here. Moving on, we also saw what we could do with SIMurai is fuzzing. And the main idea is that this proactive commands here needs to be passed somewhere. And they have a lot of complexity. And one intuition is where there are parsers, there may be bugs, and fuzzing may be helpful to find them. So our first attempt was actually not looking directly at the proactive command, but using the SIM files and having corrupted files in the file system. This didn't yield anywhere because a baseband firmware would usually read all the files it needs at the very beginning when the SIM is inserted, and then caches them and then only uses them later on demand. From a fuzzing perspective, this is not a great way to get input in and then wait. So we discarded this idea. Then we sought using proactive commands on real hardware, which also didn't work well because it turns out basebands and phones don't like when SIMs constantly send malformed inputs. They will just at some point stall, not respond anymore, and it's also not particularly scalable. So the third idea, which was successful, was using the firmware emulation platform we saw earlier in the talk and using this to fuzz the proactive command surface. This looked something like this. We have our emulated baseband, and inside the baseband, there are a lot of different tasks. You can think about a task like a process on an ordinary system. And tasks usually map pretty much one-to-one to the cellular specification, and we have one task in our target baseband just dealing with the SIM and the SIM interaction. And this task will then forward messages to different tasks required for having the cellular communication stick. For instance, AT command to communicate with the outside world, or mobility management for deal with authentication requests and similar. Then the SIM task would also talk with a so-called user task, which is, SAT stands for SIM Application Toolkit, which is a synonym for proactive SIM, more or less. So when a proactive command comes in, it goes to the user task and then is dispatched later on. And for our fuzzing campaign, we hooked up the SIM task via a custom implemented peripheral to SIMurai, dealing with all the boot up of the SIM interface so that the emulated baseband thinks there is a SIM. And then we will have a proactive fuzzing harness directly delivering proactive commands to the user task, this way bypassing this indirection of first going via the SIM, faster and better for fuzzing. Implementation of this, of course, took a while, but eventually AFL++ was running, and just after half an hour, I was shocked that it already found 7 crashes. Which is not great. So this brings us to the next demo. Let's look at one of those crashes. We found and replay them against the target. So here we spawn up firmware, which is running with the input we provide, the crash.bin, and we can see here that after restoring a snapshot and so on, it will go into the user task here and say it received a proactive command. It starts to process it. It says this proactive command is of the type send SS, so supplementary services, which can be requested by a proactive command. It goes into some decoding logic and eventually gets here to this part where there's a fatal error, PAL memguard corruption. For that particular baseband, this means a heap overflow occurred and the static heap cookie was corrupted. So we have some sort of a heap overflow here with this particular crash. We triaged all of the different crashes we had, and we identified 2 key root causes leading to memory corruptions. One was in the proactive command for sending SMSs, so the same we used before in our SIMjacker spyware reimplementation. And this were mostly data aborts, so some sort of a null pointer dereference the baseband would write to memory somewhere related to null. It still is a denial of service attack, but maybe not the most interesting. Instead, the parts in the proactive send SSS, we will see prefetch aborts and memguard corruptions as we just saw now. Prefetch aborts would happen when the baseband tries to fetch a program counter from a memory location which is not executable or not map. In other words, there's program counter corruption by the input from the proactive command, and we confirmed that we also control the program counter. So this is a heap overflow leading to PC hijack on the baseband. So these 2 key root causes, we replicated crashing inputs on physical phones, on newer hardware. The things we fuzzed, the emulated baseband was a bit an older version, and for instance, just 1 week after the release of the Pixel 8, we took the input we found from a phone from 6 years ago, and it would crash the baseband accordingly. So we wrapped all of this up, reported it nicely to the respective vendors, and they got it fixed, which is great. So no, at least not these proactive commands can crash our basebands anymore.
Yeah, so after that, we were actually planning on giving, or we were giving another talk at a different venue, and we were trying to think of like cool ways to demonstrate this proactive capability that the SIM has, and we found this interesting page in the data in the standard for launching a browser. So we can launch a browser from the SIM, and we can control the URL that the browser opens from the SIM as well by encoding it into the proactive command. So we thought like, yeah, this looks great. Let's make a demo of this and show it in that talk.
So this is how it happened. Fast forward, a year later, 2025, we were at that conference and showcasing this live. In the demo, we would have a user confirmation phase where the phone asks, want to see a magic trick? So this text fully controlled by the SIM. A user would click OK, and then it would open the browser at an attacker-controlled URL. Now, while we were preparing for this presentation, Thomas actually found something interesting at the same time. He found a bypass to this menu, this user confirmation phase, so that no clicks is needed. The browser will just open. I was, of course, shocked by this and then wanted more information, and Thomas just told me, yes, let me show you. And he showed me the technique and was very interesting. Then at the actual conference, we were also, we were not showing this on stage because we were still planning to disclose it at the time, but we were discussing with some friends of ours. And particular Jiska told us back then, hey, do you know how this interacts with lock screens? And we were thinking, hey, that sounds quite interesting. So let's have a look. We have here a phone. Lock screen is on, right? It's locked. I'm starting in the shell web server. And yeah, the SIM tray is open. I will just insert the SIM and hope. Oh, it went off. It says no service. And we do get here a request to our web server saying, I've been sent on a SIM Odyssey. So despite the lock screen here is on, the phone just visits an attacker-controlled URL, which, in my opinion, is not great, right? I don't want someone else to put a SIM in my phone and my phone visits some website. And just to show, to unlock it, right, it sent us then later to a YouTube video in this particular scenario, showing more demos from Sims, but either way. We were wondering, why does this even work, right? Like, this is a bit odd. Why does the lock screen, or first of all, why is there no user confirmation phase, and why does this work through this lock screen? So we looked again in the spec, and the standard said, unless the terminal is of type NK or type ND, which is no keyboard or no display, so if phone has both, doesn't apply, the terminal shall ask the user for confirmation using the alpha identifier, if present, when it receives the launch browser command. So in other words, if this alpha identifier is not present, it's undefined behavior. The specification does not allude to what a phone should do. We would argue the sane approach is to ask the user, but apparently some phones decided to not do that. So we tested a bunch of phones for this. And what came out at the time of testing was that it looks more likely like an actual regression in Android. Like older phones, pre-Android 14, would usually ask the user even if the alpha identifier is not present. So this was quite interesting. Anyhow, again, we wrapped this up, bundled it together, reported it, and got fixed. It's upstream on Android phones since December last year, and the actual fix landed in AOSP already in October. And what the fix does is interesting because I would argue it's a partial fix. It still doesn't check for user confirmation. Instead, what it checks is whether the lock screen is active. So if the lock screen is active, don't open the browser. Otherwise, tough luck. Which, of course, is also not great, because now we could, for instance, write an applet which just resends the comment over and over, and as soon as the user unlocks the phone, we are visiting a website again under attacker control.
OK, let's now take a look at something else. We also found, we're also reading the standard again, and we found this interesting page. So we actually can also issue run AT proactive commands from the SIM, which allows us to run AT commands from the SIM on the terminal. Seems like a bad idea. And we've also seen some previous work in papers like Attention Span, where they showed that just having AT command control, being able to issue AT commands, actually can do quite a bit of damage. So we were thinking, we had this one phone in our storage, and we saw that it actually supports this AT command, but really, like most other phones that we had, didn't support it at all. So we didn't initially think it was that interesting because of the limited exposure. But then we started looking, and we had this idea of like, OK, phones maybe don't support it, but there are also other kinds of mobile devices, like, for example, IoT devices. And this was our little light bulb moment. Let's look at that, and let's see if they actually support this run AT proactive command.
Now, the question is where to get a good sample set for IoT devices, right? Like, how can we cannot just buy something and hope it has a cellular connection and a modem built in. We need to kind of go more methodological about this. So we were looking around, and we found that Porn2Own Automotive actually has a lot of interesting IoT devices in scope, most IoT devices on wheels, but also things like electric vehicle chargers, automotive OSs, right, like which may be Android, again, SIM interaction. So a lot of interesting things, and most importantly for us, there were even documented SIM slots. There were blog posts discussing the targets of Porn2Own. So these pictures directly are from this blog post by Todd Manning. It shows us there are a couple of different targets having both a modem and a SIM slot directly exposed. So we thought that's a great way for testing this attack surface. But then we had a different issue, which is we don't have the target hardware, and the target hardware is documented where for the American market, we're not in America, and so on and so on. So we did something else. We approached our friends at Fuzzware and asked, hey, can we just use your hardware for testing? At that point in time, the people of Fuzzware attended Porn2Owns multiple times, and they have quite a lab with different hardware over multiple generations. And they were awesome enough to say sure. And even more awesome than that, they did not ship us hardware. Instead, they made us a fully remote setup available where we could control everything we wanted out from somewhere else in the world, which was great. So big shouts here to Fuzzware for helping us. So with all of those hardware, we started testing the SIM AT support on the different modems.
And vulnerable they were. We checked a bunch of different IoT devices, including also things that could potentially be in larger devices, and we saw that a lot of them are actually vulnerable. A lot of them did support this run AT interface, and well, potentially vulnerable at least. And they support this run AT interface, and we could issue AT commands to them. So to actually analyze what actually happens there. We saw proactive commands in the flow there. Run AT commands are actually very similar. I mean, they're also proactive commands, and they flow in a very similar way. First, we have the status or any APDU. Then we have the fetch, the terminal response, and then the only really difference there is at the end, the terminal or the phone or really the IoT device will issue this envelope command. Which will indicate the actual AT response. So that's essentially the flow there. And there's some weirdness to this. I mean, of course, proactive commands, I didn't mention this before, but they are actually bare TLV encoded. So this is an ASN1 encoding, fairly strange. It essentially is like a binary form of JSON. Then we also have the fact that this process is very asynchronous. It's a little bit tricky to take care of everything, but it's not that bad. More importantly, though, for the actual AT interface itself, the one that we get exposed to the card, we see some potential limitations there. So usually, when you send AT commands to the terminal for a regular for serial or something, you usually get the initial response, and then sometime later, the terminal will actually produce a proper data response. So this will happen asynchronously sometime later, and we don't get these notifications on the SIM. We only get that initial response that the AT handler produces. And then there's also the data mode. So there are some commands that require interactive input, data input. And while this is normally completely perfectly fine on a regular serial interface where you just, it flows, gets into this data mode and just give it some data, either fixed length or with a special terminator like delimiter. But from the SIM, we can't really do this. The moment that we package an AT command into a proactive command, and we ship this to the terminal over the response in the APDU, it will just stop there, basically. We won't be able to actually interact and give the data interactively to the terminal. So to analyze the actual run AT attack surface and be able to investigate whether this is actually dangerous or not, we designed some tools. So first tool that we designed is called CATI. It essentially consists of like a host app that you run, and it can run in two different modes. The first mode is the emulated mode, so we are just running software SIM and connecting this to the SIM trace, and then the SIM trace connects to the ME, so you can interactively provide software SIM the AT commands that you want to run, and it's going to process the entire state machine and produce and send these proactive commands to the terminal. The other mode is interposer mode. So if you need a data connection to a real network, for example, and you want to use a real card, you just put this into your SIM reader, like card reader, connect this over USB to your host, and then point this reader to the actual emulator, and then we will forward more or less most messages to the real card, handle some things on our end in the emulator, and then basically make it seem like the phone is connected to the real SIM, but actually we can still issue these proactive commands from the emulator. Another thing we made is for instances where you want to insert like a real research card into the target, and for that we have like a two-part kind of strategy. The first part is an applet. This gets installed onto like a research card and plugged into a target device, and then we also have a CLI that you interact with to actually kind of send commands over to the applet. So the way that this works is after you install the applet on the SIM, you pack these AT commands that you want to send into, first of all, into the APDU. Then this gets packed into a CSIM, and then that CSIM gets sent over a regular AT interface to the terminal. On the terminal, it will take whatever is parameter to the CSIM, will unpack it, and that's the APDU. We'll send it to the real card, and then the SIM will be able to issue the AT command that you want it to be issued directly to the terminal. And then the response kind of flows back into the CLI for like a little bit of a hacky mechanism, but it uses envelopes basically. And then lastly, we also wanted to automate. So we had some devices that supported this run AT interface, and we wanted to run like thousands of AT, different variations of AT commands and different also types of AT commands. So we wanted to run this and see like whether the SIM AT interface is the same as the real AT interface. And we basically have this automated tool, which we give it a kind of a list of commands we want to try, and it handles the entire state machine, communication with SIM trace, communication with the terminal, rerunning, restarting the emulator, and things like that. And then at the end, we have a nice result file that we can just easily analyze with another tool.
So let's have a look at one of these tools in practice. We decided to show CATlet, so the applet installed on a SIM here on an IoT modem, which we have. So let's go to this demo.
Yeah, in the meantime, think about your favorite AT command. Maybe we can send it to it.
Yeah, so we're running it, and here we are spawned into CATlet. And as Thomas said, we are open for suggestions. Which AT command would you like to execute? Any? Do you have any?
Let's just try AT plus GMR.
AT plus GMA. And open.
Quote.
Yeah. So we are sending this over now. We are the USB interface to the AT interface of the ME. This will unpack it, send the APDU to the SIM. The SIM will run the proactive run AT command, and then we will get a response back. And this is what we're seeing happening here. It takes a little while, but we eventually get back an answer here, nicely packed. So I think it's quite impressive to be able to do this, because this basically means we don't only have the USB interface to send AT commands, but also the SIM AT interface. Which brings us to the next part, which is, did we find interesting attacks using this? The answer is yes. Unfortunately, we can't talk about it yet. More infos in August, but think about it. You have AT control over your target with a hostile SIM. There are plenty of fun things which could go wrong. All right, now to our ongoing endeavors, like the next chapter in our SIM exploration. And we really want to do a big shout here to an LNet who is funding our efforts here to build additional tooling to explore the SIM interface. But how did we get into this? It looked something like this. One day, Thomas came again at my office and asked, hey, can I have 3 months to learn about hardware design? And I said, yeah, sounds fantastic, sure.
Yeah, again, how hard can that be, right? It's just electrical engineering, right? So we had a few ideas like what to do and how to expand the capabilities that we currently have. And one of the very first one of the ideas Thomas had very early on was using port I/O, PIO of the Raspberry Pi Picos, the RP2040, 2350 microchips, to use this to implement the SIM communication itself. Physical layer.
Yeah, on the physical layer. Then I thought, hey, if we can build our own hardware, we could potentially build our own interposers and have a lot of fun things. Overall, both of us just talked, it would be great to have more reverse engineering and more research tooling in the field. And that's how we get started with developing 3 different types of hardware editions.
Yeah, so the very first thing that we tried was actually, well, we actually implemented the PIO on physical layer, implemented the ISO 7816 spec on PIO to get physical layer control. And this kind of looked like a very simple prototype. I mean, I'm not going to bore you with that. But we wanted to do current sensing, voltage sensing, and also injecting foreign voltages into the terminal on the actual SIM interface to maybe see if there's something weird that we can do. And this eventually kind of led to probably the design of my very first PCB ever. Wasn't nothing crazy. But the thing is, we actually used a different RP. We used the RP2350 for the PCB, 2040 for the prototype, and they have a very different I/O block, GPIO block, which they don't support the same voltage ranges. So that was kind of a failure. But there's more to come. So we have also the SIM Shield. The SIM Shield is like our interposer. So we want to make an interposer that goes in between the SIM and the phone. There are some commercial ones, very difficult to program. We did reverse engineer a little bit of that, and it's just very cumbersome to get the software on. So we thought, like, let's make an open source, open hardware interposer. So the first step to getting that, because it's a very tiny device, is to make a development board. And that was kind of like the first prototype there. We found like this Texas Instruments chip, which comes in a very tiny DSBGA package. It's only like 0.3 millimeters thick. And after implementing a bigger version of that, bigger package of that MCU on a kind of bigger development board and ordering it, we landed on this. So we have a kind of fully working development board for the actual MCU and the firmware and everything that we would be running on the actual real interposer. And the next thing was, after figuring out some quirks with the schematic and figuring out how to reduce noise and make sure that handling the different voltage levels is okay, I ended up actually designing the interposer itself. And this is kind of what the PCB looks like. This literally just was like a couple weeks ago that we actually finished the design on that. We sent it off, we panelized it, we sent it off to our fab, and well, they manufactured it. And once we come back from this, we will actually get it in the mail, and we're going to be able to test it out. But yeah, that's our interposer.
Yeah, and as Thomas said, all of this is in development. We're actively working on it, and hopefully end of this year or early next year or later next year, who knows, it's hardware, it can take a while, but we hope to be able to make this available to the community. And the big question, of course, is this the end? Well, maybe the end for the presentation, but not the end of our efforts in the SIM space and SIM interface. So to recap, what we saw was SWICC and SWSIM, a SIM emulator, which is kind of the basis for all our later explorations. Then we discussed SIMurai, our framework for exploring really the dangers of having hostile SIMs. So what happens if you have a malicious SIM in your phone? Then we developed CATana, a toolkit to make the SIM AT interface explorable. And lastly, we looked into SIMcurity, our current endeavors, to create more research tooling in the space. Now, the main takeaways for this presentation are, I think really the key message here is SIM is an attack surface, and we believe it should be considered as an attack surface. It has been seen in real-world campaigns that SIMs are used for attacks, and if we care about privacy and security of our phones, we need to be able to defend us against hostile SIMs. Unfortunately, all sorts of devices which are connecting to SIMs, so phones, IoT devices, and so on, were not really built with this threat model in mind. Right? Like they're mostly considering the SIM as a trusted entity provisioned by an operator. And yeah, as part of this, right, like some of the vulnerabilities we pointed out, or some of the issues we pointed out in this presentation, like launch browsers, were mentioned in presentation years ago, and they still remain up to this day in the stack.
And many more proactive commands as well that we have not even looked at yet.
Yeah, so we believe there's more work to be done until this interface gets more hardened. And the last takeaway is a little bit more joyful, which is hardware design is actually a lot of fun. It appears maybe a little bit difficult at the beginning, but it turns out to be very fun, and yeah, we are happy to do it, and you should try it out as well. Now, towards the end of the presentation, there are a bunch of people who helped us along the way, right? Like we condensed 4 years of research journey in a 45, 50 minutes presentation. There were a lot of different people who along the way helped us. They're here on the slides, and really a big thank you for everyone who helped us here. Now, if you want to learn more about our project, these are the sources where you can follow things discussed in the presentation or things coming up. We have our academic publications. The one on CATana is still under embargo, but to be released in August. The website of NLNet gives information about the SIMcurity project, so what we are doing now. And there's also liskra.org, which currently is still a bit empty, but we plan to push updates on our hardware design as we go on from now.
Including sources and stuff like that.
Yeah. And with this, thank you for listening to us. That was our presentation. We're happy to take any questions.